Greetings and welcome to the Chemistry 223 lecture for Chapter 13, the first chapter of Chemistry 223. And I'm really glad to have you here. I believe that Chem 223 is honestly the most exciting of the three Chemistry 200 classes. All right, in 221, we kind of learned the basics and how things work. 222 got a little bit more sophisticated. And in Chemistry 223, we bring a lot of those ideas back together into a pretty cool, complete package. So anyway, I'm glad to have you here. We got some really neat things to share with you. If this is a face-to-face class where we're actually meeting on the Mount Hood campus, do make sure that you get both the Chemistry 223 companion, which is a mixture of all the different labs and problem sets and stuff like that you're going to need throughout the term, and also the lab notebook before the first lab. And the lab notebook can be just a composition book, something to keep some lab notes in while you're doing the labs. If you have both of those things on the first day of lab, you are good to go. If this is a virtual class, then obviously things will be a little bit different, where we're not meeting on the Mount Hood campus. The companion is still something which I do recommend, because the companion will have the things you'll need for learning, problem sets, labs, etc., etc. The lab notebook, though, won't be required. Regardless of if you have a virtual lab or a face-to-face lab, if you do have questions on anything, please let me know. Reach out to me, because I know this stuff can be kind of confusing, and I'm happy to help. The website for this class is mhchem.org/223. I recommend you go there and look around a little bit too. They'll have a lot of information that you'll need and stuff like that. But without further ado, let's start getting into the lecture.
If a solution of lead ions is added to a solution of chloride ions, a precipitate of lead chloride forms. The equation for the reaction looks typical. If the sample is heated, the solid lead chloride goes back into solution. The reverse reaction takes place. This is an example of a reversible reaction. In the equation for such a reversible reaction, we use a bidirectional arrow.
One factor of chemistry that we haven't discussed until now is the idea of chemical equilibrium. And in the past, we would have talked about lead ions and chloride ions making lead-2 chloride, the white solid you saw. And that would have been a one-directional, if you will, arrow. It would have been just reactants going to products. But in reality, these reactions, at least most of them anyway, it's in a state of equilibrium. And what that means is that in this case, the lead-2 chloride that forms the white solid, some of it decomposes back into the ions. And this equilibrium just means that you can't really bank on just reactants going to products, or for that matter, products going to reactants. Things are going to go both ways. And most reactions actually exhibit chemical equilibrium. You don't have just reactants going to products, or you don't have just products going to reactants. You have actually a mixture of both of them. Now, the bidirectional arrow, which is written in several different ways, is going to be really helpful to us in this class. Sometimes they look like two half arrows, and that's that version right there. So you can kind of imagine that's like two half arrows, all right? Sometimes, though, you're also going to see one like this one with two full arrows. They mean the same thing, all right, and they're just different when you can pick which one works best for you, too. But that means that you've got a state of equilibrium. And honestly, most reactions do have equilibrium. So in some ways, I feel kind of guilty starting Chemistry 223, because I've kind of been lying to you so far in Chem 221 and Chem 222, and not really lying, okay, because it's all about learning curves, man. But anyway, I haven't talked about the process of, say, products going back to reactants until now. And that's what makes Chem 223 different from Chem 221 and Chem 222. This equilibrium thing is really going to rock our world here in basically this whole quarter. And we'll see lots of examples of what you can do with it, how you can use equilibrium to affect reactions, like if you want more product or you don't want more product, there's ways to make these things happen. Pretty cool. So in equilibrium, when you have the double-sided arrow, the bidirectional arrow, you have to realize that all these equilibrium systems are quite dynamic. They're not staying in place. It's not just reactants going to products and they're being sitting there, all right? Products then are breaking up and going back into reactants. If you do have an equilibrium, then the reaction, in theory at least, is reversible. So you say, oh, I don't really want those products to form anymore. Well, in theory, there should be some way to get the products to turn back into reactants, at least to a pretty good degree. And this is something that's both empowering and it can be kind of frustrating. If you didn't want your products to decompose and you did the wrong thing, alas, maybe it would go reverse. Another thing that's interesting about equilibrium, you can really approach these reactions now from either way. And what that means, traditionally, we've written reactants on the left and products on the right. And that's the classic chemist's way of doing things. But really, if you have an equilibrium, you can think about the quote-unquote reactants as being on the right side and the quote-unquote products being on the left side. So reversible literally means you can think about reactants going to products either way, left to right or right to left, and sometimes it'll be helpful to do both. This is an example of what's called a complex ion. And a complex ion is something we're going to talk about in Chem 223. But the important part for us right now is that cobalt, the cobalt, which is in both the pink and the blue there, cobalt can make a pink form or a blue thing. And those things are the complex ions. And this is something we'll explore in this class. So when cobalt is on the left with the COH2O6Cl2, it's pink. On the other hand, if you add some chloride to it, the chlorides push some of the waters out, and you can see on the right, you've got that blue COH2O2Cl4 -2 thing. That form has a blue thing. So in the picture up there, you can see that little test tube in the ice. Right now, we have the blue form of cobalt, the one on the right, all right? However, we're going to see this reaction is reversible. Like we talked about, there's no reason for us to think exclusively as reactants on the left and products on the right. So the second reaction here now, same cobalt complexes, but now we've reversed the previous reaction. This is now the blue cobalt going to the pink cobalt, all right? So in this context, we think about it as COH2O2Cl4 -2. We'd add some water to it, ending up making COH2O6Cl2, the original pink complex, plus 2 chlorides. So this is what it means. You can literally think about it as reactant going to product from either direction. And this is like written out kind of what's happening here.
At room temperature, a solution of cobalt chloride is pink in color. When we heat it, it gradually turns blue. If we then cool the solution in an ice bath, it turns pink again. The reaction reverses.
So in this video, you can see examples of how you can transform one complex to the other. All right, so for example, if you have the pink and you add excess chloride, you can make the blue complex. On the other hand, if you have the blue complex and you add extra water, you can end up making the pink complex. And another factor that we're going to talk about in the Chem 223 is the effect of temperature. So you can see they're adding ice, they're heating it up, color changes occur. All of these are ways you can affect an equilibrium. This is a reaction we're going to talk about a lot in the beginning part of Chem 223. It's a reaction between an iron center, an iron +3, and a polyatomic ion called thiocyanide, SCN-. And the thiocyanide pushes out one of the waters to make an iron thiocyanide complex. Now, the whole reaction is listed right here in black, all right? And actually around the irons, like we're going to see at the end of Chem 223, there's actually a whole bunch of water molecules. So the SCN- is essentially pushing out one of the waters to make this iron thiocyanide complex over here, and water is a product. We're going to usually write it, though, like this one up here at the top, which is the iron +3 and thiocyanide making the FeSCN2+ complex. And this is absolutely an equilibrium, all right? You can affect this by adding more reactants or more products and changing temperatures and stuff like that. To just realize that the actual chemicals, there's water molecules involved, but we're going to see they're not quite as important as talking about just the iron and the thiocyanide making FeSCN2+.
When a solution of iron 3 nitrate is added to a solution of sodium thiocyanate, the red-orange iron thiocyanate complex ion is formed. Although the reaction looks complete, substantial amounts of iron ion and thiocyanate ion remain unreacted in solution. When iron 3 ions contact thiocyanate ions in solution, they can react to form a complex ion, iron thiocyanate. As the reaction proceeds, product molecules can react in the reverse direction to separate and reform the original ions. Eventually, the concentrations of products and reactants become constant. At this point, the rates of the forward and reverse reactions are equal, and the system is in a state of dynamic equilibrium.
The first video on the left shows what the FeSCN2 plus complex looks like. It's kind of a rusty orange, maybe red. If it's intense, sometimes I call it the Klingon blood red color. And if you're new to my teaching style, yes, I am a Star Trek person. I'll make lots of Star Trek references like Klingon blood red, but you don't have to like Star Trek to do very well in this class, so don't worry. But anyway, it's got a neat color. And also importantly is that the iron plus 3 and the thiocyanide solutions were both essentially colorless. So you go from clear solutions to this kind of orange-red thing, which is really cool. Now on the right is what's happening at the atomic scale. When the iron bonds with the SCN-, that's when you see kind of the blood red color, all right? Iron bonding to water, it just makes a colorless solution. So actually, because this is an equilibrium, it's kind of like a dance. And at first iron is dancing with water, but then, thiocyanate, and they start dancing for a while. But then iron goes, hey, maybe I want to dance with water again. So it starts dancing. Instead of dancing, of course, this would be bonding. But it's not as intense of a chemical bond, you can argue. So that's why you can kind of have this back and forth kind of interaction between things that makes this equilibrium possible. Now, in the old days, we would have just said, okay, iron plus SCN, they make a bond, makes FeSCN2 plus, and that's it. But now, in the big kids league, if you will, of Chem 223, we can see that actually this reaction, like most reactions, are equilibrium. All right, they go back and forth between the two species. So the iron-water complex becomes really an iron SCN- kind of complex, but then eventually it bounces back to iron-water, back to iron SCN, etc., back and forth over and over. So equilibrium is very dynamic. These things are changing all the time on the atomic level. At first, there's a lot of action because the iron and the SCN comes together to make that blood red / orange red, whatever you want to call it, thing. But after a while, the reactants and products kind of settle down, all right? And you still have forward and reverse reactions, but that's there's like a constant state. Once equilibrium is attained, you don't have like an excess of reactants being turned into products or an excess of products going back to reactants. It's a steady state they use in science, which just means the forward and reverse reactions kind of stabilize. And when you get to this stabilization part, that's when you're at equilibrium. There's lots of examples of chemical equilibrium around us all the time, and the easiest one is just ice with liquid water. And I'm sure everybody knows you take liquid water, put it in the freezer, it becomes ice, you can use it as ice cubes, whatever. On the other hand, you take the ice cubes out, you leave it on the desktop, and whoops, now all of a sudden the water turns into a liquid, but you can put it back into the ice form. This is an equilibrium. This is a temperature-based equilibrium, all right? And that's going to be important. We'll talk about that more. But again, that really is a type of equilibrium. Another example from geology is stalactite and stalagmite formations, all right? And these are the things sometimes if you've been in a cave that kind of are coming down from the ceiling or coming from the floor up, they're pretty cool. I don't know that much about it. I'm not a geologist, but anyway, you get the idea. This is an equilibrium with a calcium carbonate, and calcium carbonate can react with water and CO2, which is a weak form of an acid, kind of, and it makes calcium ions and hydrogen carbonate ions, and this goes back and forth, and geologists will study the behavior, why it goes back and forth. Pretty cool kind of stuff. So to talk about equilibrium, chemists and scientists use what's called the equilibrium constant. And I want to talk to you about how to describe an equilibrium constant, and we'll use this a lot in Chem 223. So let's assume that we have a system at equilibrium where big A and big B are reacting to make big C and big D. We're defining big C and D as products and big A and B as reactants. And little a, little b, little c, and little d, those are the reaction coefficients, the stoichiometric coefficients we talked about in Chem 221. So if you have this kind of reaction, then the equilibrium constant, which gets the symbol capital K, it's equal to products divided by reactants. And the products, you raise them to their stoichiometric powers, so little c and little d are applied to big C and big D. And in the bottom part, the reactant part, the reactants are also raised to their stoichiometric coefficients. So notice that big A is raised to little a, and big D is raised to little d. That's the idea here that's going on. Equilibrium constants are always effective at a given temperature. They do change with temperature, and we'll talk about that later too. But if you know this value of K, and K again is nothing more than a number, all right, you can actually predict concentrations of products or reactants for a given reaction. So knowing a value of big K is important, all right? You can do a lot of things with it. Now, because K is based on reactant and product concentrations, which are moles per liter, or moles or grams, and because in chemistry, grams can never be negative numbers, K will just be a positive number. It will always be larger than 0. It will never be equal to 0, and it will never be equal to a negative number. The numeric value of K is going to be really important to us, but I do want to point out, it's always going to be a positive number, and we'll see more about how to do this. So again, K, products divided by reactants, raise all your products and reactants to their stoichiometries. We'll see what we can do with it. This leads us to our first, what I call iClicker question, or first clicker question. If this was an actual face-to-face lecture, all right, I offer my students a way that they can participate in the lectures a little bit more by having these iClicker questions, all right? And iClickers are pretty cool. It's kind of like if you're at a game show, you can try and pick the right answer, all right, and see what's happening. Now, in this kind of lame compared to a game show lecture, what I'll do is I'll put up some kind of chemical question with answers, and you would be able to pick what you think is the right answer. And then after a small amount of time has passed, then we'll talk about what the right answer is. And I don't care if my students get the questions right or wrong, but it does help them kind of feel part of the lecture, all that kind of jazz. Now, in this virtual video lecture that you're watching right now, I don't have a method to give you extra credit, and I'm sorry about that. However, I do encourage you, if an iClicker question comes up, you can pause the video, you can work on it a little bit, think about what the right answer is, and then unpause the video, and I'll talk about in the lecture like what the right answer. So you can kind of see like how you're doing. If you can go to lectures, I do encourage you to do this, but on the other hand, in this virtual world, just kind of think about what the right answer is, and we'll go from there. So knowing that, here's the first question. Which of the following is the correct form of the equilibrium constant for that given reaction? And it's 2 SO3s going to 2 SO2s plus O2. Okay, so equilibrium constants K are products divided by reactants. And in the way that this reaction is defined, and that's going to be super important to us, SO2 and O2 are products and SO3 are reactants. So you can see, for example, answer A, in the top part, the numerator, you do have SO2 and O2, and in the bottom, for the reactants, you have SO3. But the other thing you have to do is raise the reactants and products to their stoichiometries. In this reaction, that means a 2 will be applied to SO3, so it would be like SO3 squared. You'd also do the same thing to SO2, but O2, you would have it just to the first power, and anything to the first power is itself, so people don't usually put the superscript 1 up there. So answer A is not correct because the SO2 and the SO3 in the denominator both need a squared term. So if you look, it looks like answer B is going to be right then, because you do have a 2 squared by the SO2 and a 2 for the SO3. The O2 has just an invisible 1. So this is how you describe an equilibrium constant. All right, products divided by reactants, raise them to their powers, you're good to go. If you're curious where equilibrium constants, quote unquote, come from, they in reality come from the kinetic rate constants that we talked about at the end of Chemistry 222. Now, this is a slide that's more informational, and if this is like, blah, 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 and it doesn't make any sense, then you can honestly just ignore it. But I know that a lot of you are curious about where these things come from, so let's talk about it. In Chem 222, at the end, we talked about kinetics. For a rate law, if it was an elementary reaction, then rate equals some kind of K, and if it was elementary, then it would be NO2 squared. That's assuming reactants are going to products. So notice in the first rate law, which is what this thing is right here, I added a little f. The rate in the forward direction, which is NO2 going to N2O4, would equal Kf, the forward rate constant, times NO2 squared. Now, because it's equilibrium, though, we need to think about the rate from the reverse reaction, and that's what the little r stands for. So if it was from N2O4's perspective, then you'd write rate equals K times N2O4. And again, if it's elementary, then the reactants will appear in the rate law as they have right there. So there's just a 1 because the stoichiometry is 1. Hopefully you're kind of seeing now maybe where these stoichiometries come from. So if you combine the forward and the reverse rates, and you also play with the reactants, so if you couple this with the fact that if rate in the forward direction should equal the rate in the reverse reaction, because everything is settled down like we talked about earlier, then what you can do is let those two equal each other. Kf times NO2 squared equals Kr times N2O4. Put the products in the top, reactants in the bottom, so N2O4 divided by NO2 squared, and that equals Kf divided by Kr. Remember, rate constant K's are just numbers, equilibrium, so that's where K comes from. Big K is basically the forward K rate constant divided by the reverse K rate constant, Kf divided by Kr. And if you remember from Chem 222, we definitely looked at how little k was temperature dependent. We used those to find the energy of activation, stuff like that. So the big K equilibrium constants are also temperature dependent. They're going to have different things. What's really important for you from this slide, first of all, is that this is where big K's come from if you're curious. But more importantly, use big K for equilibrium all the time, all right? Don't use little k. Little k in my world is used for kinetics, and that's a big difference and stuff. You have to have little k's for kinetics, big K's for equilibrium. Oh, joy. This graph is the concentration of reactants and or products on the y-axis. And on the x-axis, we're seeing the progression of this reaction, like reactants turn into products, stuff like that. And you can see that at first you had just H2 and I2. Those are the red and blue lines if you look carefully. And initially there was no HI. But after a while, you can see the H2 and the I2 do react, and they form the HI. And once you get to the place where basically the concentrations of reactants and products are pretty chill, then you end up with quite a bit of HI, and you don't have as much H2 and I2. This little part right here, which I put the little bracket in there, that shows the place where essentially equilibrium has been established. Product and reactant concentrations have kind of stabilized. All right, at first it was too dynamic, but then it becomes stabilized, and that's where equilibrium lies. And so equilibrium, again, it doesn't happen immediately. It takes a little bit of time. Sometimes that time can be like milliseconds, and sometimes it can be like days or years. It's hard to say, but always there is going to be a little bit of time as reactants and products kind of stabilize with each other. The reactant concentration will decrease all the time, and the product concentration will increase all the time. All right. In this particular example now, the products, as you see, are at a higher level than the reactants, and that will be important to something we'll talk about here in a little bit. In the equilibrium region, in the part where the little square bracket kind of thing is, we would write the equilibrium constant K as the HI, the product, and it would be squared because of the stoichiometry of 2, and we would divide it by both the H2 and the I2. H2 and I2 have the invisible 1 out there, so it would just be 1. Anyway, scientists have actually studied this reaction in considerable depth, and they have found that the equilibrium constant K is 55.3. And again, usually people don't record the units of big K, just like we didn't usually record the units of little k in Chemistry 222 for kinetics rate constants, if you remember. And if you don't, it's totally fine too. Just realize that most of the time K, the units are not included. If you do include them, that's fine, but if you don't, it's no big deal. Here's a reaction. NOCl is a fairly reactive compound. 2 of them will break down to 2 NOs and a Cl2. This is an equilibrium though. So while some of the NOCl will break down to NO and Cl2, some of the NO and Cl2 that form will reconverge into NOCl. This is the joy of equilibrium. So in this problem, we start with 2 moles of NOCl in a 1 liter flask. And at equilibrium, we calculate or find that the NO concentration is 0.66 moles per liter. We can use this information actually to calculate the value of K, okay? And K, remember, is just a number. It's going to be products divided by reactants. We have to describe what K is, but we also want to make sure that we use the equilibrium concentrations of products and reactants. We don't want to use the initial parts. If you have an equilibrium problem where you want to solve for an equilibrium constant K, you need to set up what we're going to call an ICE table. And ICE is an acronym. First of all, when you set up an ICE table, you want to put reactants followed by products. So reactants on the left and products on the right. So for this reaction, NOCl would be the one reactant, and NO and Cl2 would be the products you can see next to it. And then ICE, the I of ICE stands for the initial. And most of the time in these ICE tables, we're going to use moles per liter. So NOCl, we start with 2.00 moles in a 1 liter flask. That means the initial concentration of NOCl, 2.00 moles per liter. On the other hand, we don't start with any NO or Cl2. If you read through that problem, it says at equilibrium, we find some NO, but we don't start with any NO. So both NO and Cl2 are 0. But because this is equilibrium, products will be formed from the reactants. That's what equilibrium is. You've got some of everything. So in the ICE table, the C stands for the change of going from the initial to the E, the equilibrium part. So ICE, initial, change, equilibrium. At equilibrium, that's where we have 0.66 moles per liter NO. We didn't have any to begin with, but now we have some, all right? So an ICE table, initial, change, equilibrium on the left, and then you put reactants and products on the top part right there. Now, if you think about this long enough, if NO went from 0 to 0.66, that means the NO concentration changed. It increased by 0.66 moles per liter. So the change is literally the change between the equilibrium and the initial part. And NO went from 0 to 0.66. That means it changed by 0.66. You can't get something from nothing, all right? The 0.66 had to come from somewhere. And the 0.66, the change in NO, came from the NOCl breaking down. So NOCl broke down to make the NO. And you can see from the stoichiometry of the reaction up above, 2 NOCl's make 2 NO. So if 0.66 moles of NO were made per liter in this reaction, and the stoichiometry is 2 to 2, that means that the NOCl had to go down by 0.66. Again, you can't make something from nothing. So NaCl went down by 0.66, while NO went up by 0.66. This is where knowing an equilibrium concentration is really helpful, because if it started at 0, you can see how much it went up, and you can see also then that the NaCl went down by 0.66. Now, the equilibrium is literally initial, and then you add the change to it. So in this case, it was 0 plus 0.66 to get an equilibrium of 0.66 moles per liter NO. But for NaCl, that's going to be 2.00 minus 0.66. We can calculate the equilibrium concentration of NaCl. It's 1.34. It's 2.00 minus 0.66. So knowing the concentration, the equilibrium concentration of NO, allowed us to calculate the equilibrium concentration of NaCl as well. But we're not done yet. Remember in Chem 221, for every 2 moles of NO that were formed, you also end up with 1 mole of Cl2. NaCl doesn't just make NO, it makes Cl2 as well. And if it made 2 amounts of NO, then Cl2 will be half that number. So if the NO increased by 0.66, then the Cl2 went up by half of that. It went up 0.33 moles per liter. Again, it all comes back to that stoichiometry again, that 2 to 2 to 1 ratio. 2 NOs that are made means that 1 Cl2 is made, or 0.66 divided by 2 essentially is 0.33. So at equilibrium, this is going to be 0.33. You can always use stoichiometry to figure those equilibrium values out if you want to. So as an example of this, let's take the 0.66 moles of NO per liter, and there are 2 moles NO per 1 mole Cl2. You can see that's where the 0.33 number comes from. It literally is the stoichiometry. You can do the same kind of thing, and you can find the change of NaCl. You can also say 0.66 moles per liter NO per liter have formed. There are 2 moles of NO formed for every 2 moles NaCl that break down. So you can see 2 over 2 is like 1 to 1. That means that the change number is going to be 0.66 for the NaCl. It has to go down. That's the source of this reaction. That's why it's negative, but it is the same kind of thing. So these changes are based on stoichiometry. If you look at the change line, it's a 2 to 2 to 1 ratio, 0.66 to 0.66 to 0.33. That is 2 to 2 to 1, just like the stoichiometry. However, it is also reactants versus products. The reactants in this side are negative. The products in this side are going to be positive. You're always going to have a line like that between negative and positive. Sometimes the products will be decreasing and the reactants will be increasing. You don't have to think about these as reactants going to products. You can think about them as products going to reactants. So, all being said, these are the numbers you should get. You can use stoichiometry to do it, which is fantastic. You can also kind of figure it out in your head, but this is how they figure out the equilibrium parts. It's the equilibrium line that we're going to use to calculate the value of K on the next slide. The initial parts just tell us how much are there. The change tells how things are being affected. And again, change level is going to be affected by stoichiometry. And again, remember that one side will be negative and the other side will be positive. So the products here are positive and the reactant is negative. And then you can calculate the equilibrium concentrations, and those are the numbers we're going to throw in our value of K. In this reaction, K, products over reactants, K is going to be NO squared times Cl2, the products, divided by the reactant, NaCl, and we'll square that one as well. And again, we want these equilibrium concentrations in that K value. So it's going to be 0.66 for the NO, and we'll square it, times 0.33, the Cl2. We'll divide it by 1.34 squared. Throw that in your calculator. 0.080 is the equilibrium constant. Woohoo! So we introduced the ICE table, which is going to be really important to us in the next couple chapters. Initial change equilibrium. We saw how the change line is affected by the stoichiometry. So we're still using those balanced equations from Chem 221, just in a different way. And the equilibrium concentrations are the ones that go in the expression for K. And you can figure out then values of K from there, stuff like that. Good to go. When you're writing an equilibrium constant K, there are a couple of rules that are helpful to remember. First of all, you never put solids or liquids in equilibrium expressions. So in the example right there, which is in the formation of sulfur dioxide, sulfur is a solid. It's reacting with oxygen, a gas, to make a sulfur dioxide. Notice that sulfur is a solid. So in the equilibrium constant, we're not putting the solid in there. It's just SO2 divided by O2. Solids and liquids never appear in equilibrium expressions. This one's going to be more like a lot of the examples we're going to see where water, a liquid, is excluded. And again, remember, solids and liquids never in the equilibrium constants. So this reaction is ammonia, NH3, reacting with water. It makes ammonium, NH4+, plus hydroxide. Water is a liquid at room temperature, so it's usually not included in equilibrium constants. Products over reactants, K would be ammonium times hydroxide divided by ammonia. But again, no water, solids and liquids always excluded from K expressions. Here's a question. Which of the following is the correct form of the equilibrium constant expression for this reaction? This is the reaction potassium and water, making potassium hydroxide and hydrogen gas. Okay, so the idea is equilibrium constants are products divided by reactants. But the other thing we want to focus on here is that solids and liquids are not placed in the equilibrium constant expression. So you'll note here that potassium is a solid and water is a liquid. So neither of those will be in the equilibrium constant expression. We will put in the solutions, the AQs, the KOH on the product side, and we'll also put in the gases, the H2. So in this K expression, you'd have KOH squared on top times H2, the aqueous and the gases. But in the denominator, since everything is a solid or liquid, you would just have like 1, the number 1, like nothing is in the denominator. You don't put a 0 there because that would make your K values go crazy. Math people, and divide by 0 freaks everybody out, okay? So in this case, K and H2O, you wouldn't put them in there. You just have like an invisible 1. So if you look at all those options, answer E would be the correct one here. You'd have KOH quantity squared times H2, and in the denominator, because K and water were solids and liquids, you would just have a 1 right there. So that also brings up another thing. If everything on the reactant or the product side is solid, liquid, whatever, just put a 1 there. Only put aqueous and gaseous things in your equilibrium constant expressions. Another thing you can do with equilibrium constants is you can add equations or reactions together to give you a new expression. So let's see how this works. Here's the sulfur plus oxygen making sulfur dioxide reaction we looked at a little bit ago. Let's call this equilibrium constant K1, and it's SO2 divided by O2, again keeping the solids out as well as liquids if we had any. No problem. However, this reaction actually does go on to make sulfur trioxide. So if sulfur dioxide reacts with half of an oxygen, i.e. 1 oxygen atom, but oxygen's a diatomic that have no fear of ice clear brew things. Anyway, half of an oxygen to make sulfur trioxide, we have now a second equilibrium. And in this new equilibrium, products divided by reactants, nothing is a liquid or a solid, so we don't have to worry about that. K2 would be SO3 divided by SO2 times O2 to the 1/2 power. So again, notice here the stoichiometry was 1/2, so we raise it to the 1/2 power. The square root of oxygen is the same as O2 to the 1/2 power, and we'll talk about this later. So just as a quick reminder from math, something raised to the 1/2 power is like the square root, all right? We'll come back to that in a future part. Anyway, Let's say that we wanted to go directly from sulfur and oxygen to sulfur trioxide, i.e. ignore the SO2 intermediate, if you will. Well, no problem. So first of all, the K net for our overall reaction would be just sulfur trioxide divided by O2 to the 3/2 power, all right? And if you look carefully, if you took K1 and multiplied it by K2, it's going to give you this net reaction. I don't believe you, Dr. Russell. Oh, whoever said that, random student in the back of the room, I totally understand. So K1 is SO2 divided by O2. And K2, excuse me, is SO3 divided by SO2 and O2 to the 1/2 power. So we're multiplying these both together. You can see the SO2 divided by SO2 cancels out, so no SO2. And we have here an oxygen to the 1 power and an oxygen to the 1/2 power. In math, you can combine these into O2 to the 3/2 power, and the SO3 is still there. So literally, multiplying K1 times K2 will give you the K net, the one that you want, and the SO2 is kicked out. So if you have two equations and you combine them to give a net equation, overall K is going to be just the product, i.e. multiply the old K's together. I don't usually like using fractions, and if you've taken classes with me before, I will go like, oh, chemists hate fractions, but sometimes with heat of formations we have to, et cetera, et cetera. So let's say that we have an S plus 3/2 O2 making SO3, and the old K, as we saw a little bit ago, was SO3 divided by O2 to the 3/2 power. But let's say I said, oh, get rid of fractions. Chemists hate fractions. No problem. So you can multiply the whole equation by 2. All right, so if you multiply that, you get 2S. 3/2 times 2 is 3 O2s, and then 2 SO3s. The new K, though, as you can probably imagine, is going to have a different form. So notice that the new K is going to be SO3 squared divided by O2 to the 3rd power. Well, if you take the old K, this thing up here, and you square the whole thing, notice how this is the same idea. It's like the old K squared. So we multiplied everything through by 2 to get the new K expression. And if you had an old value for K, you can turn it into the new value by squaring it. So let's say that K old was a value of 10, and we wanted to figure out the value of K new. Well, no problem. We would take the old K, 10, and square it. 10 squared, the new K would be 100. All right? So you can literally transform a K value into a new K value if you multiply the stoichiometries together. So if I said multiply everything by 2 to get rid of that fraction, you could absolutely translate your old K into a new K. So this is kind of a trick of the trade, which can be really helpful. Finally, you can also change direction of an equilibrium constant. So instead of thinking about sulfur plus oxygen going to sulfur dioxide with K equals SO2 divided by O2, again, remember to keep the solids and liquids out, let's say we wanted to reverse it, and we wanted to think about it from sulfur dioxide's perspective, breaking down to sulfur and oxygen. Okay, no problem at all. The new K would be the oxygen gas on top divided by SO2 on the bottom. Again, no solids and liquids. And if you look at the old K versus the new K is just 1 over the old K. If you went 1 over SO2 divided by O2, it would become O2 divided by SO2. So the new K is just 1 over the old K. All of these transformations can be found in greater detail in a handout I have called Manipulating Equilibrium Constant Expressions. It's in the companion, and it's also online. If you can't find it, let me know, and there's examples of how this works. But the real important message of this section is that if you are working on a lab, all right, and you're thinking about it as sulfur dioxide breaking down to sulfur and oxygen, you're going to have some value of K. And maybe in my lab, I'm thinking about it as sulfur reacting with O2 to make sulfur dioxide. Well, our K values should be different from each other. all right? We can translate one lab's work into the other by going 1 over the K to get the other lab's K. But by default, the numbers could look very, very different. And this is something in chemistry you have to be very aware of. Everybody has to use the same form of the equation for the answers to make sense. You can, and sometimes it'll be better to think about it as SO2 breaking down or forming SO2 from the reactants, either way. But you can translate one into the other as long as you're hip to how these transformations happen. So it's a good kind of section to pay attention to. Here's a reaction. The compound N-butane is breaking down to isobutane, and it's an equilibrium. Isobutane is also known as 2-methylpropane, or just methylpropane if you want. But anyway, the K value here, 2.5. Well, let's say you wanted to know the value of the reverse reaction. So notice how isobutane was the product. Now isobutane is the reactant, and the N-butane is shifted as well. So to go from an old K to a new K, where it's the reverse like we've done right here, you just want to go 1 over the old value. So to figure out the K value here, you'd go 1 over 2.5 in your calculator. That number comes out to be 0.40. So that's how you would calculate the new value of K. It's 1 over the old one in this case. Remember that K values will never be negative and they won't be 0, so answer C is just kind of silly, but this is how you can translate one K into another. All of our equilibrium constants so far have been technically a K sub C, and a K sub C is the most common kind of equilibrium constant. It's an equilibrium constant based on molarity, or moles per liter. But there are other kinds of Ks, and we're going to look at some of them in this whole class. But one that's definitely worth talking about is what's called a Kp. If you have an equilibrium constant that's a Kp, it's an equilibrium constant based on gases. P stands for pressure. And if you remember from Chem 222, atmospheres are the dominant pressure term used in chemistry. So a Kp, instead of using moles per liter, which is what we've been using so far, we would use atmospheres of gases. So Kp is only applicable towards gases. You really can't have a solution pressure per se, although you can argue osmosis, but that's a different story. But anyway, almost all the time Kp is atmospheres-based pressure equilibrium. Kc is moles per liter, and you can have gases, so many moles and so many liters of volume, all right? That's totally fine. Gases can be Kcs or Kps. Solutions, though, aqueous things, pretty much just Kc. Now, when it comes to atmospheres, it's really important to remember that 760 millimeters of mercury equals an atmosphere. So if you're given a pressure in millimeters of mercury, make sure you translate into atmospheres before you do any Kps. Here's an example of 2 different ways you could write this reaction. This is nitrogen and 3 hydrogens making 2 ammonias, and this will be something we'll talk about more. If you're going to write it as a Kc, that's a moles per liter based equilibrium, you would write it as square brackets, which means moles per liter of ammonia squared on the top divided by nitrogen times hydrogen to the 3rd power. We're raising everything to the stoichiometries. But in this case, you could also have a Kp. Everything there is a gas. So you could have the pressure of NH3 squared divided by the pressure of N2 times the pressure of hydrogen gas to the 3rd power. Either way is fine. And remember, Kps, you have to use atmospheres. Kcs will all be moles per liter. You can translate a Kp into a Kc if it's the same reaction, and this is the conversion you would use. Kp equals Kc times RT raised to the delta N. So let's talk about how we would do this if we had to convert Kc into Kp, or Kp into Kc for that matter. First of all, T is the Kelvin temperature. Anytime you've got gases, you've got to use Kelvin temperatures. So that would be that 273.15 plus the Celsius temperature would give you the Kelvin temperature. R is the gas R, the 0.082057 number. And the units for that are liters atmospheres per mole Kelvin. You would not want to use the other R, the energy R, which we will use in other parts of the lectures. Delta N is the change in moles of the gas. Remember, delta always means final minus initial. So that would be the final moles of gas minus the initial moles of gas. So as an example, if we're looking at that same reaction where nitrogen and 3 hydrogens combine to make 2 ammonias, delta N would be the final moles of gas, 2, minus the initial, and there's an invisible 1 by the N2, so 3 plus 1 would be 4. So you can see that delta N in this case is -2. Delta N's can be positive numbers, they can be negative numbers. Once in a while there's 0 if you don't have any change in moles of gas. There's all different kinds of possibilities here. So this is actually now a new type of equilibrium constant. We looked at Kc, moles per liter based equilibrium, which is by far the common one we're going to use, but this is a Kp, an atmospheres based equilibrium constant. This is another handout that I recommend you have access to. It lists different types of equilibrium constants that we might see in Chem 223. We're going to see several different kinds of equilibrium constants as we go through the next chapters. And if you forget later on what a Kp is, which is totally fine, go back to this list. It'll tell you what it is, and you can go from there. The actual number that's associated with K will tell you if the reaction has more products or if it has more reactants. If your actual numeric value of K is larger than 1, that means you have a product-favored equilibrium. And that means that at equilibrium, you're going to end up with more products than you have reactants. On the other hand, if your K value is less than 1, that means you're going to have a reactant-favored equilibrium. And at equilibrium in those cases, you're going to end up with more reactants than you have products. Now, a couple of things. K, again, is never going to be 0 or negative, all right? K, if it's less than 1, will be a number larger than 0, but less than 1, okay? If K is larger than 1, it will, of course, be larger than 1, but it can go up really, really high, and we'll see numbers that are really, really big. Also, we're going to see some Ks that are really, really small. So just FYI, always positive numbers, but they are all over the place. Here's an example. That reaction we looked at earlier with nitrogen and 3 hydrogen gases making 2 ammonias, the K value, which is a Kc by the way, 3.5 times 10 to the 8th. So ask yourself, is K larger than 1 or greater than 1 or less than 1? And definitely this K much greater than 1. So that means this K is going to be a product-favored equilibrium. And once equilibrium is established, we would expect there to be more ammonia around than you'd have nitrogen and hydrogen. So again, look at the value of K, and this K is much larger than 1. You're going to have a product-favored equilibrium, more ammonia, less N2 and H2.
Nitrogen monoxide does not react with water. When it contacts oxygen in the air, however, the reaction is almost instantaneous and produces the brown gas, nitrogen dioxide. The reaction is so product-favored that a chemist would say that it has gone to completion, a fact reflected by its very large equilibrium constant.
Product-favored reactions are good to go. You see something instantly when they react, and that's a really cool thing. Now, it is still a little bit based on kinetics. All right, kinetics is literally how fast and slow things go, but usually, assuming the kinetics are reasonable, which most of the things we look at are, okay, then you see something happen, all right, like you see the brown gas here forming. So product-favored are usually what people want when they're trying to make something. Here's a reaction. It's silver chloride, which is a solid, and it's breaking down into the ions, silver plus and chloride. So this K, which is a Kc now, because these are solutions, the silver ion concentration times the chloride ion concentration, 1.8 times 10 to the minus 5, a pretty small number. Now this K, as you can see, is a lot less than 1. So that means that this reaction is going to be very reactant favored. favored. Once equilibrium kicks in, you're going to have more AgCl solid around than you're going to have silver ions and chloride ions. So again, literally the value of K will tell you if K is greater than 1, more product. This K is much less than 1, so we're going to have more reactant. Remember, K will never be 0 and never be negative, but they can get really, really, really small. This is a pretty small one. That means you're going to have more AgCl than you'll have Ag plus and Cl minus. We talked about earlier, if you flip a reaction, reactants become products, products become reactants, you go 1 over the old K to get the new K. So you can also think about this reaction as silver ions and chloride ions making AgCl, solid, all right? If you do that, to find the new K, you would go 1 over the old K. It would be 5.6 times 10 to the fourth. So notice by flipping the reaction, K becomes greater than 1, product favored. So in this version down here, K is greater than 1, product favored. You'd expect AgCl to dominate over the Ag plus and Cl minus. On the other hand, up here with the initial reaction, K was much less than 1. That means you'd expect more reactant, AgCl, than Ag plus or Cl minus. So both ways tell you the same thing. But because K is different, that also is just a highlight for me and a warning. Make sure that you always write equilibrium constants in the same way, because reversing a reaction will give you what looks like a different number. The chemistry is okay. It's just you have to realize there's different ways of thinking about it. Here's some graphs that show what happens when you have a product favored or reactant favored K. If you have a K greater than 1, then that means that your products here on the left will be in a bigger concentration, y-axis, than the reactants, all right? That means more products, less reactants, K is greater than 1. On the other hand, if you have a K less than 1, then you have more reactants than you have products, all right? So you can see in this graph now, reactants started high, and they did go down, but they didn't go down nearly as much as the product side, as the product favored K did. Notice that in both reactant and product favored, you do have reactants and products, all right? Nothing is 0 in these, but it's the relative amounts that make the big difference. So the left-hand side, product favored K greater than 1, the right side, reactant favored, more reactants than products form, K is less than 1. Here's some reactions. First one, 2NO2 is going to N2O4, K value 180. The second one is iron 2 hydroxide, FeOH2, a solid, breaking down to iron 2 plus and 2 hydroxides, K value 7.9 times 10 to the minus 15th. And it says which statement is true. So only one of these apparently. So A, both reactants are product favored. Remember that for product favored, you must have a K greater than 1. The first one is definitely the case. K 180, that's larger than 1. So A is definitely product favored. But B, the second reaction, 7.9 times 10 to the minus 15th, that's much less than 1. That one's going to be a reactant favored K. So A is not true. The second one is not product favored. And likewise, B is not going to be correct either, because while B, the iron 2 hydroxide reaction, is reactant favored, A, the first one, the NO2 reaction, is very product favored. So if you look at C, it says reaction A is product favored, reaction B is reactant favored. That sounds good to me. Answer C would be correct. And again, to answer this problem, you literally look at the value of K. If K is larger than 1, product favored, K less than 1, it's reactant favored. Pretty chill.